Hello, I'm Devon Merrill. I'd like to talk to you today about a system that I've been working on for a few years at UC San Diego. It originally started as a way to implement electronics automatically, but it's expanded to multiple domains, software, mechanical, and I think it could potentially be used for other domains too. A little outline of the talk, pretty standard. So why would you want to implement electronics automatically? So as an engineer, my time is split between lots of different projects. I'm out of school. I'm kind of known to that you can go to me and I'll help you with your electronics project, but there's just too many, and it's all through all these different departments. I'm sure all of you have ideas for electronics that, oh, if I could just magically have this electronic, it would be great. But you don't have the skill or the expertise, you don't know the person to get that embedded system. And you can't just have new students or new engineers added to a project. We've probably all heard of the mythical man month. Adding people to a project doesn't mean it goes faster. And especially in an academic context, you have a student, they have to get up to speed on the project, they don't really know the area, they don't know who is in the department, and if they're doing a 1 quarter or 1 semester project, their iteration time is they might get 1 or 2 out before they have to move on to the next project. And just as an engineer, I know that a lot of my time is spent doing stuff that I've done a million times before. I've written this glue code or something very similar to the glue code before, or I've designed the same power circuit. Maybe it's very slightly different voltage or different supply current, but everything is almost exactly the same. So it seems like it's ripe for automation. And as an educator, so this is a picture of some fashion students at a local community college. And I taught a class there where they embedded electronics into garments. Now this is about a quarter of the class, and I think in the whole class, maybe 3 people owned laptops. So I wasn't going to be able to teach them how to use traditional CAD tools or engineering tools to design their design circuit boards. I had to do it for them. And there's no way I could have done it in the few months that I had to work with this class. So there are a lot of students that could benefit from using electronics in their projects, and it's just not feasible from an instructor time standpoint. So we've heard about a lot of computational design systems, and I'm sure you're aware of many others. My kind of overview of them is that they're all domain hyper-specific. So there's really cool computational design systems for, say, stuffed animals or certain types of furniture or all these different things. And what's interesting to me is that you can't add parts from multiple domains. They're very specialized in their one particular domain. And the key to that is that they all have this very fixed topology. It's either a fixed topology or a very regular topology with many repeated units. And just as an overview, this is kind of what my view of a design and fabrication system is. You start with this design specification from the user, say the form that they want the fabricated thing to take, and then that's fit into the topology of the system, the computer model of what the design is. And then there's some processors that work on it that make it into a fabricatable thing. And so I say this first part is the computational design point, and of course there's feedback between all these parts. And then the user is doing the computational design, and then there's this back-end system that does computational fabrication. So my proposal and what I've been working on is adding a little piece in here that makes it multi-domain. And it's an algorithm based on decision trees. Doesn't look very exciting there. Okay. So the key thing is that almost all of these systems, or when I'm designing systems, is you have these building blocks and you have to connect them together. So Legos, erector sets, electronics, the very interesting robotic primitives that can be assembled into bigger robots. They all are these little components. And there's interfaces that you connect together. And I've noticed that there are these interfaces, and some of them are required for the component to function, and some of them are provided and can be used to allow another component to function. So for example, an LED, right, it's a light. It needs power, and so it has this interface where it requires power, and maybe a battery provides that interface. And what we'd like to automate is synthesizing automatically the connections between these components, and maybe also adding some components from a library. So this is the decision tree for designing something with my system. So the initial design, it starts with those yellow functional components. So it's lights, wheels, sensors, things like that. It doesn't contain anything that the user doesn't care about. So batteries, microcontrollers, they don't add anything functional to the device. So the system has to add those components and then make connections between all the components. So every decision in this tree, starting at that root with no added components and no connections, either adds a component or a connection. And you get this really large tree of partial designs, and they're partially connected or they have components added to them. And a lot of those decisions say you add a battery, you add another battery, you add another battery. They never will lead to a viable design. Only a few of them will. So how do you search this really large tree fast? Because there's a huge exponential explosion in the number of designs. And there's a lot of details in the paper you can read, but the key things are these search heuristics. So of course you want to prefer cheaper designs. I found you have to rate the connections based on how difficult they are to connect to other connections. So a very specific a component with very specific voltage requirements is more difficult to connect than a component with very general input voltage requirements. Or say a robot arm that has a very specific attachment point is more difficult to connect than a robot arm that has a conformal attachment point. And of course, you want to avoid the dead ends that you found in the tree. So I've used this system to create a lot of different artifacts, and I'm continuing to integrate this system into different projects. One of the projects is this class that I've been teaching to first quarter freshmen, and they design and build a robot from scratch with a custom circuit board. Now, without this system, as the TA of the class, there's no way that I could create the several dozen robots in one quarter. But using this system, we can create dozens, and we have created hundreds of robots using this. The students will draw what they want their circuit board to look like. They drag and drop some components, and then that's the functional specification. And then our system will add more components, make the connections between the components, and create a CAD file that we can send off to a manufacturer and get the circuit board back along with complete assembly instructions and an API that allows them to not worry about pin assignments or the specific registers of the microcontroller. It's just LED turn on or wheels turn on or wheels move backwards. And it's been very successful. So these are some of the latest batch of robots. And it's really enabled the creativity of the students. So there's a parallel class that's being taught where they build a robot from a kit. And this is in the electrical engineering department. And I'm in the computer science department. Now, the electrical engineering class, they build a robot from a kit, and all the robots look the same. And all the robots do the same thing. They kind of follow, they do the line following project, and they do the pick up a block project. But like say this robot here, the students, they didn't have to think about, well, do I connect this wire? Do I need this many batteries? The system took care of that. So they were able to learn how to use a laser cutter to make cool wings for their dragon. Or they had time to learn how to use a 3D printer and create a cool head for it. Here's another one of my favorites, a little Bulbasaur, and the flower kind of blooms open. And so they repurpose some of the components. Here it's a gripper component, and they turn it up and they made it into a blooming flower. And so in the fashion class that I taught too, I couldn't design custom circuits for all of the students. It would take way too long. So I was able to say, well, how many lights do you need? And then the system would take care of the rest. It would say, this is how much power you need. This is the microcontroller you need for how many channels of lights you have and things like that. So here's a couple images of garments that the electronics were designed using the system. And like I said, it can be extended to other domains. So this is a robot arm, and the top is the specification for the robot arm. And the bottom is what the system designed and then we fabricated. So you can see there's a base and a gripper. And if there is a barrier in the way, when the system tries to complete the gripper, it will start adding segments onto the robot arm from the gripper, trying to get to the base. And if there's a barrier in the way, it'll design the robot arm to go around it. And if you say, well, so this one in the middle on the bottom here, we said, well, we want the robot arm to be able to pick up a heavier object. So the system automatically added a stronger motor as the last segment. And it all uses, the key thing is it all uses the same interface specification. There's just Python objects, and if you can fit the domain into these required and provided interfaces, then it will just work with the system. And using those heuristics, we can get the search time down from never completing with 2 levels of that tree. These trees go down to 40 levels with some of the more complex electronics, and they complete in a few minutes. You don't want to see the math. Okay, so this is some of the mixed domain designs that we've had. So the top layer, the top pictures there are the specifications for the bottom fabricated results. So all the user has to do is say, this is what I want the body of the robot to look like. They drag and drop some functional elements, lights and wheels and legs. And the system can automatically design the circuit board. So for the wheeled robot, it added extra motor drivers for the 4 wheels. For the 2 wheels, it said I only need 1 motor driver, which is those little red things. But it knows it has to balance because the control API for the 2-wheeled robot says I need a gyroscope to be able to balance. So it added a gyroscope and connected it. And for the legged robot, it doesn't need a motor driver of the same type. It added a bunch of servo controllers to control the servo joints. And then the body of the robot automatically has the attachment points for those wheels and legs embedded into the 3D printing file. So it's all automatic. You just drag and drop for the 3D specification, and then you get out 3D printing files, source code, circuit board, schematics, and everything you need. Here's some more examples of complex electronics that I can design. So a thermostat, 3D printer, and a musical sequencer device. And the top level, again, is the graphical specification. A user can just drag and drop functional components. And then the bottom, it has these added non-functional elements, so power systems and motor drivers and analog to digital converters and things like that. So if you know what you need your device to do, that's enough to have to get out easy to follow assembly instructions and all the manufacturing files. Here's a system that I just got working, and it kind of shows that you can add, once you have this core of specification to implementation, you can start playing with different ways of specifying. So I drew the outline of a circuit board, and then I used stickers to place the components, and then that directly translates into a functional circuit board. And this was a rejected short talk, but I still get to show the slide. Okay, that's my last slide. Thank you very much.